Let me see if I can't help you out here. You say you were able to solve for AC, you were able to solve for CB and AB successfully, but you're struggling with BD and BE. I think you didn't mention whether or not you solved for CE. But if you solved for these values over here, I'm not sure if you actually solved for DX or EX and EY. I guess the best way to do this is probably to just solve for the whole thing. My first step is usually solving for the angles, but since, everything is equidistant, I'm assuming we're working with just 2. These might be factors of 10, but it still ends up being, everything ends up being a 45-degree angle in this example, it looks like. And so we can just skip that step, and the next step is to solve for our moments. And so this is 500 pounds going down, and this is 500 pounds going down. And since there are 2 reactionary forces here, we can assume that this is the pin. It's obvious that this is the pin right here. And how do you get 1,000 and 1,500 here and here? Well, we'll call this reactionary force at E in the Y direction, and we'll call this one reactionary force E in the X direction. And over here, we've got reactionary force at D in the X direction, because this is clearly where the roller goes. Okay, now how do I know if this is going to the right or this is going to the right? We'll get to that in a second. I do know that the sum of all forces in the Y direction have to add up to 0, and the sum of all forces in the X direction have to add up to 0. Well, there are 3 forces in the Y direction. I've got 500 pounds, and reactionary force at E in the Y direction. I know that these 2 500 pounds are going down. Therefore, I know Ray has to be going up with 1,000 pounds. We can do the algebra on this if you want to. We would say 500 down plus 500 down plus Ray equals 0. And since these are both going down, you can treat them both as negative. In other words, I can say Ray equals 500 pounds plus 500 pounds. Therefore, Ray equals 1,000 going up. So that is how I get reactionary force at E in the Y direction. How do I get reactionary force at E in the X direction and reactionary force at D in the X direction? Well, I use my moments to figure that out. And so where are my moments? And I guess I'll use yellow to represent the moments. Since the pin is right here, we'll draw our little pin here. That means my moment at A is going counterclockwise, and my moment here at C is going counterclockwise. And so I'll call this moment A, and I'll call this moment C. Now, the sum of all moments, so if I say the sum of all moments has to equal 0 as well, so that's going to equal moment A plus moment C, and that's also going to add moment at D, because that is the only other place where a moment can happen. You can't have a moment at your pin, and there is no force, there's no outside force on B to create that moment. The reactionary force at D in the X direction has to create that sort of clockwise moment to counter those two. And so we say counterclockwise moments are positive, clockwise moments are negative. So in other words, I could say minus moment D instead of plus moment D, and then just add moment D on both sides of my equation. I don't like doing this. I usually just set all my clockwise moments equal to all my counterclockwise moments, but you can do the algebra if you want to. Anyway, we say, hey, that moment D equals moment A plus moment C. And hopefully this is kind of intuitive. Again, I don't know if you actually solved this part or not. You didn't mention reactionary forces. And so it should be intuitive that if you have these 2 forces pushing down on this truss, it would want to push down. Something has to be pushing back. And if you imagine a wall right here, then this force, this reactionary force at D, is pushing back and sort of up. It's causing this truss not to actually fall. Again, hopefully this is intuitive to you. If it's not, I can link to other YouTube videos to help explain this concept a little bit better. But basically, the moments have to cancel out. Since you have two counterclockwise here, this one has to be going clockwise. And the only way it can be going clockwise is if RDX is pushing to the left at D, which means REX, it's a little check mark right there, has to be going to the right. And so I know REX and RDX have to cancel out. So I can even write that out. REX plus RDX will add up to 0, because that's the definition of the sum of all forces equals 0. And so I will use this equation, but how do I solve for these two values? Well, that is where the sum of all moments equation comes in. And so the moment at A, I'm not sure what your distances are. You haven't included that. I'm going to go ahead and assume that each one of these is just 1 foot, from one distance to the other. If it is more than that, it doesn't matter as long as they're all equal. So if all of these were 100 feet or if all of these were 5 feet, the math would end up canceling out anyway. So just to keep the math simple, I'm going to go ahead and assume that these are all 1 foot. And so how far away is moment D from my pin? And the answer would be, in this case, it would be 2. And so I would say I don't know the reactionary force at D in the X direction, but I do know it is multiplied by 2 feet to create this moment. And that has to be equal to moment A, which is 500 pounds, is the force times its distance from the pin, which is 1, 2, 3, 4 feet. And that is added to moment C, which is also 500 pounds, times 2 feet from the pin. And so what do we get here? Well, we get 500 pounds times 4 feet would be 2,000 foot-pounds, plus 1,000 foot-pounds. And that is equal to, I'm going to go ahead and add that dot there. That is going to be equal to, again, root x, as I call it affectionately, RDX, or reactionary force of D in the X direction, times 2 feet. Okay, and this simplifies to 3,000 foot-pounds. And what can I do? Well, I can just divide by 2 feet on both sides, and I'm running out of room here. Feet cancels. 3,000 divided by 2 is obviously 1,500, so we get RDX has to equal 1,500 pounds to the left. And again, I know it has to be going to the left because if it was going to the right, it would be a counterclockwise moment, which is impossible because you have to have something to cancel out these two counterclockwise moments. So it has to be clockwise. So that's how I know root x is going to the left with 1,500 pounds of force. And since I know Rex has to cancel out root x, it also has to be 1,500 pounds in this case to the right. And so that is how I get these two numbers. Okay, so what else can I solve for here with this information? Well, if I look at just the sum of all forces in the X direction at D, there are only 2 forces at D. And actually, before I start solving for the individual joints, I like to draw my free body diagram. I know the previous commenter mentioned that you can assume that all the forces are tension. I actually don't like to do that. What I like to do instead is I look at each individual joint and say, what is going on? And what's going on at D is we have a leftward force of 1,500 pounds. Okay, and what does that mean? Well, that means I need a rightward force at D to cancel out that leftward force. And how many things can apply a rightward force? Well, the only thing that can apply a rightward force is BD. So BD has to be pushing to the right at D, and if it's pushing to the right at D, it intuitively has to be pushing to the left at B, meaning BD has to be compression, aka negative tension. Okay, so I know that BD has to be compression because it's the only other force acting on D in the X direction. We cannot make that assumption yet at BE, for example, because there's a lot of X and Y forces here. And so I actually kind of skip all of these over here for a little while, and I come over here to A, and I say to myself, well, I've got a downward force at A. Well, what can apply an upward force at A? Well, clearly AC can only go in the X direction because it is going in the X direction, but AB does have a Y component. So if it has a Y component, we can use that Y component to make it go up. In this case, if it's going up, it has to be going to the left as well. So it has that left component and it has that up component within its own vector, which means it can cancel out that down component. Okay, so that means if AB is pushing up into the left at A, it has to be pushing down and to the right at B, meaning AB is also under compression. Now we have a leftward force at A, and there's only one thing that can cancel out the leftward force at A, and it has to be AC going to the right at A. You have to create that free body diagram where all forces cancel out. If you have something to the left, you have to have something to the right. Now, again, if it's going to the right at A, it has to be going to the left at C, making it under tension. At C, we can assume the exact same thing. I now have a leftward force at C, AC. Therefore, CE has to be going to the right. That's CE. Now, if it's going to the right at CE, I have to assume that it's going to the left at E. Therefore, CE is also under tension or, negative compression. If you look at C, there is a downward force of 500 pounds, and so I can assume that I have to have an upward force at C of 500 pounds, which is what we call BC, and that has to be compression. I think you figured that out. You also were able to figure out that this was 500 pounds, you said, and you deduced that this was 707 pounds, 707 pounds. And I'm assuming that's because you realized the Y component of AB would have to be 500 pounds, and the X component of AB would also have to be 500 pounds, and you just did A squared plus B squared equals C squared. You got 707, or maybe you used your angle of 45 degrees, your sine, cosine, tangent. You figured out these three numbers. This should be drawn better. That says 500. Hopefully this makes sense. So yeah, you said you were able to figure all these out, and we'll talk about how to figure out the rest of the numbers in a second, but hopefully this is obvious to you. How do you know that if you have a rightward force, you need to cancel out with a leftward force? It's a little bit harder to solve for these joints where there's so many forces in the X and Y direction. Like, for example, at E, we've got a leftward force at E. Through CE, we've got a rightward force at Rex. We have this other force here at E that we don't know yet. And so you can't just assume whether it's going to the right or the left when you have more than two. But if you only have two forces in the Y direction at C, then you know they have to be equal and opposite to add up to zero. The same is true here. If you only have two forces in the X direction at C, you know they have to be equal and opposite to cancel out. And since there's only two members at C in the X direction, that's kind of how you figure that out. And so with that in mind, we can assume that CE is also 500 pounds of tension here. And we can assume that because if C is being pulled to the left with 500 pounds, it has to be being pulled to the right with 500 pounds, or it is not canceling at C in the X direction. You didn't mention whether or not you solved CE, and so I'm assuming you did, but I'm not sure, so I covered it anyway. But with that in mind, we can make the exact same assumption down here with BD, that this also has to be 1,500 pounds. Why? Because there's only two forces in the X direction acting on D, and that is this force to the right at D and this force to the left at D. So they have to cancel out with, equal and opposite force. So therefore BD has to be 1,500 pounds, canceling out this 1,500 pounds. We can also deduce that DE is 0 pounds of compression or tension. It doesn't really matter which one you call it there. It is just 0. And so you could draw your arrows really either direction because there is none. And how do I know that? Well, I know that the sum of all forces in the y direction at D has to equal 0. And there's only one force acting at D in the y direction, and that is DE. And so I can say it equals DE. And so that's it. That's the end of my equation. DE has to be 0. That's how you get this number over here. So hopefully all of that was obvious. Before I solve for BE next, because that's really all we have left, let's look at, for example, how we know the direction that it's going, whether or not it's compression or tension. Like I said, I don't like to assume that it's all tension and solve for it that way. I like to just look at my free body diagram before I learn my numbers, and it's kind of obvious. So for example, I don't know left or right at E. It could be left or right. How do I know? Well, I know that E is going to the left and going to the right. Okay, so I'm not really sure what's going on there. I mean, I am because I looked at my numbers for a second, so that kind of gives it away. But let's pretend like we don't know those numbers yet. I do know I have an upward force with reactionary force at E in the y direction. Therefore, I need a downward force at E. Now, that might confuse you because you're looking at this upward force at E as well, but that's 0 pounds. But okay, let's say that's confusing to you. We can also look down here at B. We have figured out that these two forces have to be going down at B. Where is the upward force at B? If you only have downward forces at B, then B has to be falling down. Something has to be pulling B back up, and the only thing left to pull B up is a force of tension, and it's pulling up and to the right. I wouldn't have assumed it was going to the right because I had one left and one right, but I do know it has to be going up, and if BE is going up, it has to be going to the right as well, and if it's going up and to the right at B, it has to be going down and to the left at E, giving you that downward force to cancel out Ray. And so I know that BE has to equal tension. Okay, what can I do with this information? Now, well, I know it's tension, which tells me the direction of the arrows. I can really solve for BE from either joint B or joint E from here. And how do I do it? Let's just do E again. And so how do I do that? Okay, I draw E. And what do we have at E? And I might scroll down just a little bit, I think. What do we have at E? We have Rex going to the right with 1,500 pounds of force. We have reactionary force at E in the y direction, or y, of 1,000 pounds of force going up. We have 0 pounds of force going up or down right here, and so we can draw that if we want to. We could say 0 pounds of force through DE. We have a leftward force of CE of 500 pounds at E. And we have some down and to the left force that we have yet to calculate, which we call BE. And these are all of our forces in the X and the Y direction. Since this is 0 pounds, we can go ahead and ignore it. Let me actually grab my tool, and I'm going to go ahead and delete that real quick. I'm going to redraw this free body diagram now. Actually, you know what? The fastest way to do this is probably just to copy this. Control V. I'll grab this and move it right over here to redraw this, and then I can grab my rectangle tool. I can delete this, and I get rid of that too. And so to redraw this, what I'll do is I will draw out vector BE here. And BE has a Y component, so I'll call this BEY. And it has an X component, which I will call BEX. And why is this so important? Because the Y component is canceling out this upward force, and the X component is helping cancel out these two xward forces. So I can redraw this BE arrow with just its independent components. And so what are its independent components? It is just BEY, and it is, of course, BEX. Now, if I look, I only have one upward force and one downward force at E, and so I know that the sum of all forces in the Y direction has to equal 0. Therefore, BEY plus 1,000 pounds has to equal 0. And since 1,000 pounds is going up and BEY is going down, I can then assume that BEY equals 1,000 pounds. And so, okay, I know BEY is 1,000 pounds, and I know that this angle is 45 degrees. I can then use sine to solve for vector BE. And so how do I do that? Well, I'll say the sine of my angle, which is 45 degrees, is equal to BEY, which we just said was 1,000 pounds, divided by vector BE. And so to solve for this, I'll multiply by BE on both sides, and BE cancels out on the right, and then I can divide by the sine of 45 on both sides. And so what do I get? Well, I get vector BE is equal to 1,000 divided by the sine of 45. And if you type that into your calculator, you should get 1,414.2 pounds. We could have also assumed that BEX, since we know it's going to the left, and we know we already have 500 pounds and 1,500 pounds going to the left and right, we can say, well, the sum of all forces in the X direction equals 0, which equals 500 pounds to the left, plus BEX to the left, plus 1,500 pounds to the right. Therefore, we know that BEX also has to equal 1,000 pounds. That's also kind of intuitive because of the 45-degree vector, that both the x and the y component would be equal. But then we could do, since we know that this is also 1,000, a squared plus b squared equals c squared, and you would have also gotten 1,414.2. And so that's how we get 1,414.2 pounds of tension for B.